Look at this circuit layout. It is actively rerouting and optimizing its own physical geometry, driven by a machine intelligence that has moved beyond answering isolated text prompts. This is an AI system executing complex, multi-day hardware design entirely on its own. This is the result of Qwen3.8-Max, a foundational model built on a scale of 2.4 trillion parameters. For the first time at this scale, the weights for this flagship Max-class model are being released fully open to the public. Engineering autonomy requires a transition from passive context extension to active system-level feedback. Achieving this requires a system built for decoupled reinforcement learning, active gradient variance suppression, and continuous watchdog feedback loops. Addressing these structural hurdles allows an open-weight model to iterate on its own performance across software, research, and physical silicon design. Deploying a 2.4 trillion parameter model creates a direct tension between representational capacity and inference speed. Running every weight for every token would be computationally prohibitive for enterprise workloads. This diagram illustrates a sparse mixture of experts topology. When a data token enters, a routing mechanism illuminates a specific subpath of nodes. Out of 2.4 trillion total parameters, only 95 billion are activated per token, resulting in an activation ratio of 3.96. Even with a sparse foundation, scaling reinforcement learning across multi-day engineering projects often causes training to collapse due to task complexity. This was addressed by decoupling the training environment along 3 orthogonal axes: task length, workspace topology, and the interface harness. Decoupling these variables allows environment growth to scale combinatorially. The model learns to navigate hierarchical repositories natively without needing bespoke integrations for every tool. To maintain consistency across these environments, the system requires a universal reward system to unify verification. The reward function unifies deterministic execution, like checking if code compiles, with multimodal rubric grading for visual and text-based outputs. The third component is an agentic inspector that acts as an active auditor against reward hacking. If the model attempts to cheat a test or bypass a sandbox, the inspector identifies the shortcut and applies an absolute -1 penalty, invalidating the reward. However, mixing tasks of wildly different difficulties creates massive inter-batch gradient variance, which can destabilize the neural network. This is stabilized by an online data balancer. It modulates the sampling distribution of training batches to minimize the difference between the batch gradient and the true gradient. This mechanism suppresses gradient variance by over 60%. Maintaining this stability is what allows the model to undergo weeks of continuous RL scaling without policy degradation. Neutralizing reward hacking and mathematically suppressing gradient variance are the prerequisites that enable multi-day autonomy in production. This training framework was tested in a 16-day autonomous run on the open oh-my-cli GitHub repository. Without human intervention, the system generated 265 commits and resolved 151 individual issues. The agent manages this volume through an issue state machine. Tasks transition sequentially from being ready to leased by an agent, through active implementation, and into verification. The verification stage consists of a 4-stage self-testing suite: build, unit test, end-to-end integration, and desktop lifecycle validation. Complex end-to-end tests often throw unexpected exceptions, which typically cause autonomous agents to stall. To prevent this, the Qwen harness employs an automated watchdog mechanism. When a test fails, the watchdog captures the error traceback and routes it back to the agent node. This trace is re-injected into the context window, triggering an autonomous self-repair cycle and a new verification run. Over 16 days, this iterative loop allowed the agent to evolve new capabilities directly from community feedback signals. Systemic autonomy relies on the capacity to ingest runtime exceptions and iterate toward a functional state without human intervention. The model's reasoning was pushed further into the domain of digital hardware design, specifically creating a cryptographic accelerator. In a sandboxed environment, the agent had to maintain functional correctness in simulation while minimizing the physical silicon area. This chart tracks a 500-turn design trajectory. The logic gate count dropped from an initial baseline of 8,298 down to just 678 gates. At turn 22, the model shifted its focus from syntax refinement to structural reengineering. The model identified the high area cost of a hardware divider and re-architected the entire block into an iterative shift-subtract state machine. This single move eliminated over 6,000 gates. The final code was then validated through a physical place and route flow using the 45-nanometer process. The physical die area shrank from 106 microns square to just 46 microns, an 81% reduction in the silicon footprint. The design achieved time enclosure at 500 MHz with a positive 0.66 nanosecond setup slack. Translating algorithmic rewrites into verified physical silicon parameters proves the model's reasoning transcends abstract software and maps to strict physical constraints. This cross-domain depth is supported by a 51.7 score on RecreationBench, where the model recreates desktop applications from black box GUI interactions alone. In a year-long strategic simulation, the model generated a 4.16 times return on initial capital by autonomously negotiating with suppliers and managing risk. It also demonstrated autonomous scientific discovery, reproducing a research paper, and then evolving a method that surpassed the original results by 2.7 points on the AMEI benchmark. These outcomes are the direct result of the 95 billion parameter active MOE efficiency, variance-suppressed RL training, and continuous watchdog execution loops. The results from Qwen3.8-Max demonstrate that multi-day engineering autonomy is now achievable within a flagship open-weight architecture.